Now we'll be dealing with one of the important deformation mechanisms, that is creep. So before going into creep deformation, let's try to understand it using some day-to-day examples. Let me give some examples to you why creep deformation becomes important in our lives. The first example is a tungsten filament bulb. These kind of bulbs are nowadays absolute. They are not used anymore, but at least 15 years before they were used in a large numbers. So in this tungsten filament bulb, we used to have a thin tungsten filament, and you know that tungsten has a very high melting point. And when electric current is passed through it, there will be a resistive heating of this tungsten filament, and because of heating, this filament used to produce light. After certain usage, this filament used to break. So what's happening when you put this tungsten filament for a sufficiently long time? Is there a fusion or a melting? So let's look at why tungsten filament bulb used to fuse. Now, let me give another example of turbine blades, and you might be aware that these turbine blades are subjected to well below its yield stress. So after a certain period of time, these turbine blades are used to produce some cracks here, which I have shown, and there will be defects which are produced in these turbine blades, and you no longer can use these turbine blades. As you have put these turbine blades well below its yield stress, you expect that there should not be any plastic deformation, but still these turbine blades used to deform. Now let me give another example from the nature, and you would have seen in this era of global warming that there are glacier movements. There is a huge mass movement of this snow which gets discharged from the main icebergs, and this happens with over a period of time. So these glacier movements get unnoticed and there is a sudden catastrophic deformation which occurs. Now let me give another example. Example from a lead pipe sagging. So this lead pipe were used for water transportation in UK, and at room temperature these pipes used to get sagged. So there is a sagging of this pipe when you put these pipes for a certain duration of time. Now what do you find common in all these examples? So you find that the deformation is occurring after a certain period or after a certain service of that component, and the time is an important factor. Now you can see that in all these cases you see that there is a temperature which also plays a role. You have tungsten filament which is being heated. Here also in turbine blades we subject these turbine blades to a high temperature. What about glacier movements? As I mentioned, we are talking about a global warming. And what about lead pipe sagging? They are used at room temperature, and we'll be looking at why this lead pipe sagging happens even at room temperature. So let us define creep. So in all these examples, the deformation occur through creep. So creep is derived from a Dutch word that is kruipen, and which means that move slowly and carefully in order to avoid being heard or noticed. So in all these examples, the failure gets unnoticed. So here we can see a catastrophic failure occurring suddenly, and that gets unnoticed during the service. So we define creep as a mechanism which is being unnoticed if you are not careful enough. Now let's move on and try to understand creep in more detail. So let's understand creep using a plastic deformation of crystalline materials. So we have low temperature behavior of crystalline materials and we have high temperature behavior of crystalline materials. So let's talk about low temperature and high temperature now. So here in low temperature, the strain which is developed in a material is a function of stress. And a high temperature behavior, the strain is not only a function of stress, but it is a function of temperature as well as time. And now what do you mean by high temperature? Let's define that high temperature, what exactly it means. Here there are three elements which I have put: lead, aluminum and iron. Now melting point corresponding to them is mentioned over here, and you can see that it's a melting point in degrees Celsius. 327 degrees Celsius for lead, aluminum 660 degrees Celsius and iron is 1538. And let's consider a room temperature which is 25 degrees Celsius, and you can see that this lead, the melting point, you have to convert it into Kelvin actually. So when you convert these melting points into Kelvin and try to see that what will be the room temperature for them. So for lead it comes out to be 0.5 Tm. For aluminum it comes out to be 0.32 Tm, and for iron it comes out to be 0.16 Tm, where Tm is the melting point of these alloys in Kelvin. Mind you, when you are trying to relate the melting point with the room temperatures, we always go for Kelvin. Let me write it down here. So you should always go for Kelvin. So I define high temperature as a temperature which is greater than or equal to 0.4 Tm. A Tm is the melting point of an alloy or a metal. So let's define high temperature. Then this is the definition of high temperature. That is T greater than or equal to 0.4 Tm. We'll be looking at why 0.4 Tm in subsequent slides. And let me define another parameter which is a homologous temperature. And this homologous temperature is nothing but T upon Tm, which is a ratio of an operating temperature with its melting point. So this is an operating temperature T, and this is the melting point of an alloy or a metal. And the ratio of it is called as homologous temperature. Now let's understand why we need high temperature operations. I can simply explain it using an efficiency of a heat engine, and you must have studied in your thermodynamics class that efficiency of any heat engine can be given as 1 minus T2 upon T1. Where T2 is absolute temperature of heat sink and T1 is absolute temperature of heat source. This is a typical efficiency which you get when you consider heat engine. So as you can see that the efficiency of heat engine can be increased if I decrease this ratio. That can be done if I increase T1, that absolute temperature of heat source, or the operating temperature. If I increase the operating temperature, I increase the efficiency of an heat engine. So that is why we need high temperature operations. Now let's look at what are typical high temperature operations. Here let me give two examples of aero engine and power plant. So here the temperatures used are for aero engines goes more than 1000 degrees Celsius. For power plant it is something around 750 degrees Celsius. And design life, so how much the component are put it in service for how much duration. So here in case of aero engine it is 10 to the power 4 hours, and while in case of power plant it is around order of 10 to the power 5 years. So typically this comes around more than an year, something around 1.5 years. And what are the operating stresses which you use for this aero engine and power plant? For aero engine they are around 10 MPa, and for power plant they are around 100 MPa. So you can see that we operate these components at sufficiently high temperatures and for a sufficiently longer time. So you want that component should not fail when they are put it in service. So we want to increase the design life, and thus we need high temperature, and we want material which can sustain this high temperature for a sufficiently longer time. And let's define what exactly creep is. In previous slides, you have understood that creep deformation is a time dependent, and it's a time dependent continued plastic deformation. It is not an elastic deformation, it is a plastic deformation. What do I mean by plastic deformation? So when I deform material plastically, that means I cannot go back to its original shape. So this is a time-dependent continued plastic deformation which occurs more or less at a constant stress or a constant load and at constant temperature. So this is a definition of creep. Now let's look at how this deformation happens. So we keep stress constant, which is much less than yield stress of a material, and we take temperature which is typically greater than 0.4 Tm. And let's consider this component which is being subjected to a constant stress in a tensile mode, and let's plot what is a plastic deformation. And measure of plastic deformation is a strain. So let's plot the strain with time. And what are you keeping constant? You are keeping stress constant and temperature constant. And now we'll be seeing at how the strain or the plastic deformation happens for this material. So you can see that the strain gets accumulated, and you get typically such kind of strain accumulation over a period of time, and at the end material breaks or fracture or rupture. So this deformation which is occurring immediately at time t equal to 0 when we subject this material at a constant load, so there will be an instantaneous deformation. So this strain which is developed in a material at t equal to 0, we call it as an instantaneous deformation. And what happens at this location? Here the material fails. So we call this as a creep rupture, where T is equal to Tf, where Tf is nothing but a time for rupture. Now you can see that I can write this strain accumulation or a plastic deformation accumulation in terms of a strain rate. So this is a strain rate, or I can say that the strain accumulation over a small period of time dt, and we can integrate from t equal to 0 to t equal to Tf, it's time to fracture, And this is happening at a constant stress, constant temperature, constant surface energy, constant stacking fault energy, etc. And if we integrate, we get what is a total plastic deformation with respect to time when you keep all other parameters constant. So this is called as a creep curve. And let's understand creep curve in more detail. So this is a creep curve which we have got, where we have a strain which gets accumulated over a period of time at a constant stress and at a constant temperature. Now this is t equal to 0, this is t equal to tf, and you can see from the shape of this creep curve, we can divide this creep curve into 3 regions, and we call it as stage 1, stage 2 and stage 3. So this region where you have a strain which is increasing in this fashion, we call this as a primary creep or a stage 1 creep. Now in this region you can see that strain or a plastic deformation gets accumulated more or less linearly with respect to time, and this we call it as a secondary creep. And in this region you can see that the strain or a plastic deformation is accelerated, or you can see that the sudden increase in the strain or the material is deforming fast, very fast. This region is called as tertiary creep or a stage 3 creep. Now in our previous slide we have seen that we can understand this creep deformation with respect to strain rate too. We have seen that accumulation of strain rate or accumulation of plastic deformation over a period of time, and or we can understand creep using a strain rate or a creep rate. And that can be done by just differentiating this curve with respect to time to get this strain rate variation with respect to time. So we can plot a strain rate variation with respect to time, and let's do that. So you get typically something like this shape curve, and this is called as a U curve. It has a shape of a U. And now you can see clearly in this strain rate versus time plot, we can easily distinguish what are primary, secondary and tertiary creep. So you can say that in this region or a primary creep region, you can say that you have initially very high strain rate, but as the time progresses, the strain rate decreases. And in secondary region, you can say that the strain rate reaches a minimum value and it more or less remains constant. There is no change in the strain rate. And as again the time progresses, or when you put a component for a sufficiently long duration, in this stage where the material starts deforming drastically, and you can see that the strain rate increases drastically and material fails over here. So this region is based on a strain rate, also called as a transient creep rate. Why this is called as transient? If you go back and check the meaning of transient, it's changing. So here there is a change in strain rate drastically, and that is why this region is called as transient creep rate. In this region, you don't see any change in strain rate, and that is why this is called as a steady state creep rate. And you see that there is an increase in the strain rate, and that is why it is called as an accelerated creep rate. You can see that the creep rate or strain rate is accelerated. For most of the engineering applications, we focus on this steady state creep rate or the secondary creep region or a stage 2 region. And this parameter, that is a steady state creep rate or a minimum creep rate, is used for designing of a creep resistant materials. And you can find this minimum creep rate by finding out what is the strain accumulated in this region and what is a time needed for accumulation of this strain. And if you find out delta epsilon upon delta t, you get a minimum creep rate. Now let's understand why this nature. So here in this case, the strain hardening dominates. So as we deform material, the materials start resisting the moment of dislocations and there will be a strain hardening. We have dealt with strain hardening in more detail in our previous lectures, and you can see that as strain hardening dominates, the strain rate decreases. Why strain rate decreases? Because there will be accumulation of dislocations which resist each other's motion, and thus the strain rate start decreasing. While in this region, there will be a balance of strain hardening and a softening mechanisms. So which are softening mechanisms? Softening mechanisms such as recovery, recrystallization, grain growth, etc. So there will be a balance of strain hardening and other softening mechanisms. And that is why we reach a minimum creep rate, which is a constant. which is a steady state. Thus, we get a steady state creep rate or a minimum creep rate in this region, which is also called as a secondary or a stage 2 region. And what happens in this region, that is an accelerated creep rate region, you can see that there will be a formation of defects or internal cracks, and which leads to the accumulation of stress or increase in the stress concentration at a specific locations, and which lead to the fracture or a rupture of the material. So this is what we have looked at, a creep curve in this fashion and a creep rate or a strain rate plot with respect to time. Now let's move on and let's understand what is effect of stress on creep deformation. We have seen that we find out the creep behavior at a constant stress and a constant temperature. Now let's understand what is the effect of stress. We have seen this creep curve, that is a plot of strain with respect to time, and let's consider that we are increasing stress by keeping a parameter constant, that is a temperature is constant here. And you can get another creep curve if I increase a stress over here. And let's mark these three regions which we have seen, that is primary, secondary and tertiary regions on this curve, or stage 1, stage 2 or stage 3 creep regions. And you can see that if I increase a stress, you can find out the material fails at a lower time or much earlier when the stress is lower. So this is a higher stress and this is a lower stress, and you can see that when I subject my material at a lower stress, it will deform at this region or after this time. However, if I subject it for a higher stress, the material will rupture at much earlier. Also, you can see that these three stages also have shrunk. So here you can see that the stage 1 is occurring for this much period, but for this sample which is subjected to a higher stress, the stage 1 is occurring at a lower time. Similarly for stage 2 and stage 3. So you can say that what is the dependence on stress? We know that applied force provides a driving force for dislocation moment and diffusion of atoms. As I increase an applied stress on a material, it provides a driving force for dislocation moments, and thus there will be a larger strain accumulation or a larger plastic deformation that much material will see. Also, it enhances the diffusion of atoms, and thus material fails early. Now we are interested in a steady state creep rate, that is a creep rate at stage 2. And when you consider a creep rate at stage 2, and when we plot that with respect to sigma, you can see that for a steady state creep rate, it shows a linear variation. And we can write this relation, that is ln of strain rate, which is at steady state region, is equal to ln of k1 plus n ln of sigma, where n is the slope of this line, and that is linear feet of steady state creep rate versus stress. And this is n is called as stress exponent. Now, if you consider this relation, we can write this relation in this format, where I can write the steady state creep rate is equal to k1 sigma to the power n, where n is stress exponent and k1 is constant. So this is called as a power law creep or a dislocation, and this is an empirical equation. What do I mean by empirical equation? So it doesn't have any theoretical backup, or it is not being formed using any theory. It is just formed because of some mere practical observation or experimental results. Now we have seen an effect of stress. Now let's see an effect of temperature. So here what I'm doing here, that we are keeping stress constant, and now we'll increase the temperature. So we have this creep curve at certain temperature, and we increase temperature, and you see that the strain or plastic deformation occurring at higher temperature more than which has occurred at lower temperature. And also you can see that when you mark these three regions for this creep curve which are obtained at different temperatures, so this is at higher temperatures and this is at lower temperature, you can see that it has a similar effect when we increased a stress. You can see that what is the dependence on temperature. Why this is happening? Let's understand. Because this mechanism of steady state creep depends on diffusion. So we can write this steady state creep rate is proportional to exponential of minus QC upon RT, where QC is activation energy for creep. Now why are we writing this relation? because we know that diffusion in an Arrhenius form is equal to T naught exponential of minus QD upon RT, where QD is an activation energy for diffusion. As we know that we are increasing temperature and there will be a diffusion which plays an important role during the deformation, we can use this form to write a steady state creep rate with respect to temperature. And this is valid because here is a plot which shows an activation energy for self-diffusion, that is QD, and here an activation energy for high temperature creep, that is QC. And here the elements are arranged with their increasing melting point. So you can see that tungsten has a very high melting point, and you can spot some other elements such as alpha iron, aluminum, lead, etc. And you can see that this plot is versus QD and QC with an increasing melting point. And this QD is proportional to QC. And that is why we can write this relation. This relation remains valid when we consider temperature effect. So you can see that as D is a function of T, and D becomes significant at temperatures greater than 0.4 Tm. And that is why homologous temperature, which is of 0.4, becomes an important. So that is why creep deformation becomes important when the operating temperature is more than or equal to 0.4 Tm. Now we can write the combined effect of stress and temperature on steady state creep as A sigma to the power n exponential of minus QC upon RT. So in previous slide we have seen this relation, that is steady state creep rate is a function of stress to the power stress exponent, and here we are writing that steady state creep rate as a function of temperature, and we can combine this and find out what is a steady state creep rate because of the change in stress and change in temperature. And with this I will stop here.